Let's look at this problem. We have this uniform 30 kilogram slender rod. It is pinned at point O, and it is subjected to a 60 Newton meter couple moment counterclockwise. So as a result, it is rotating with a counterclockwise angular velocity omega of 6 radian per second. And we need to determine the tangential and normal components of reaction the pin O has on the rod, as well as the angular acceleration of the rod at this instant. So we start with drawing the free body diagram. I'm just going to draw the free body diagram directly on this sketch so that I can get the length relation correct. This is point G, which is the gravitational center for this rod. And because this is a uniform rod, point G is right there in the center. This total length is 0.9 meter, which means that point G is 0.45 meter from the edges, which also means that it is 0.15 meter from the rotation center, point O. So at point G, we have the weight force W equals to 30 times 9.81. And then at point O, we will have two force components, but in which directions we should draw the force components. For that, we actually need to draw the kinetic diagram first. So because the rotation is counterclockwise in this direction, therefore this is our tangential direction. So this is our MAGT, and then the normal direction always points towards the center of rotation. So this one is my MAGN, and of course I will have the counterclockwise rotation, so IG alpha. So that's the kinetic diagram drawn in red color. So with that, it gives me a hint of the force components at point O. So for the force component, let me delete that so that I'm not crowding the graph. We will have a normal component that is a normal component that is to the left, that's my ON, and then the vertical component OT. So now this free body diagram has completed. So the correct way, of course, is to draw the free body diagram separately. Again, we will have the weight force W, OT, ON, and then the free couple moment, 60 Newton meter free couple moment. And then again, the kinetic diagram will be MAGAN here, MAGT here, and then IG alpha. So with that done, now we can start writing our three equations of motion. We will have resultant force along the normal direction, which equals to ON. That's the only one along the normal direction. And that equals to MAGN. But because this is a problem involving rotation about a fixed axis, we can rewrite this equation into M omega square R. M is the mass of the rod, which is 30 kilogram. Omega is 6 raised to the second power. R, this R is from point G to the rotation center. Therefore, that is 0.15. So from there, we can solve for ON, basically just evaluating this part, and we get ON to be 162 Newton. Next, we summarize the force about the T direction. The tangential direction, we have OT and then minus the weight force, 30 times 9.81, and that equals to MAGT. Again, because this is rotation about a fixed axis, we can rewrite this into M alpha R, which is 30 times R 0.15 times alpha. So from here, we cannot evaluate anything. We cannot evaluate alpha or OT, which means that we need an additional equation, we need a moment equation. We have two options, two reasonable options, even though we technically can't summarize the moment about any arbitrary point. We can summarize the moment about point G, which equals to IG alpha, or we can summarize the moment about point O, which equals to IO alpha. Because our two unknowns, ON, OT, pass through point O, therefore we summarize the moment about point O. This way, two unknowns, OT and ON, do not show up in our moment equation. So resultant moment about point O, counterclockwise, is positive. We have the free couple moment, 60 Newton meter. And also the weight force is creating clockwise rotation. So negative 30 times 9.81 times the moment arm is the same R, the location, the distance from point G to point O, the rotation center, and that is 0.15 meter. So on the right hand side, we will have IO alpha, which can be determined from IG using the parallel axis theorem. So for a uniform slender rod, the mass moment of inertia about its own gravitational center, about this axis passing through point G perpendicular to the screen, that is 1/12 ml squared. So we will have 1/12 times 30 times the total length, 0.9 squared, plus mrg squared, that is the parallel axis theorem part. So 30 times 0.15 squared alpha. So as you can see, on the left hand side we can evaluate this. On the right hand side we only have one unknown, which is alpha. So from here we can solve for alpha, and alpha equals to 5.87 radian per second squared. And then if we substitute that into the second equation, the only remaining unknown is OT, and OT can be evaluated to be 321 Newton. So now we have evaluated the normal and tangential components of the support force at the pin support point A, as well as the angular acceleration of the rod. And that solves this problem.